So we're jumping straight to 11-2. We're only gonna be covering contingency tables. I like to include this in our class because what it does is it includes some ideas, especially when we're getting ready for the final. This section is kind of like a review for the final, I like to say. So anyway, yeah, I'll just keep it in this view, I guess. So we now consider methods for analyzing the contingency tables, which include frequency for categorical data arranged in a table. So when you read this sentence, this should remind you, I know it's a distant memory, but it should remind you of what we did previously in chapter, I want to say chapter 5, when we were doing it. Like, remember those tables that we made? Well, in a few moments when I get to the slideshow, you'll see something that may or may not look familiar. But yeah, the goal here is to decide whether two variables, random variables, are independent of each other. So hopefully that'll make more sense in a moment. And so what we got here is, let's see here, just moving things around. Okay, so yeah, example, finding expected frequency in a contingency table below. So this is an example of a contingency table. And we have in the first column, it says surgery, weight-bearing cast, non-weight-bearing cast for 6 weeks, non-weight-bearing cast for less than 6 weeks. So these are obviously different choices you can have, that you have available to you if you have I guess a stress fracture in a foot bone. And some statistics were recorded to decide whether each of these treatments was a success or a failure. So the two variables are the treatment and the results. Those are the two variables, and we want to decide whether the success or failure depends on the treatment. Okay. So yeah. So yeah. So what do you? So if I'll just pause right now. Like, what do you think? Just going with your gut. We'll do this with statistics, but just going with your gut. Yeah. What do you think? Does success or failure depend on which procedure is used? Okay. Well, anyway, so yeah, the idea is that, yeah, it looks like there's, like when I look at surgery, there's 54 successes, 12 failures. That seems pretty good. In general, it seems like, oh wait, except for weight-bearing cast, more failures than there were successes. So maybe that's not a good idea, but everything else, at least there's more successes than failures. But this is where I'm just really going on an intuitive level here when I say that. Why isn't this working? All right, so okay, so contingency, that was an example of a contingency table or a two-way frequency table, and it counts categorical data as opposed to quantitative data. See how these are not numbers but rather categories. And the second variable is used to categorize the columns, a test of independence. We hypothesize. So this is the hypothesis. This is going to be the null hypothesis. We hypothesize that the variables are independent and test to see if there's sufficient evidence to say otherwise. So we're going to assume that the choice of which procedure you choose is independent of whether it's a success or a failure. So in other words, it doesn't matter which procedure you choose. And then we're going to see if there's enough evidence to say otherwise. And let me get through this notation page, and then I'll come back to the chat and see if there's any questions are coming up. So feel free to type them in now. After this slide, I'll take a peek and see what you're thinking. But yeah. So before I look at the chat, it says notation. So this is some language I'm going to be throwing around. The following symbols will be used. O, that's not a 0, but the letter O represents the observed frequency in a cell of a contingency table. And then E is the expected frequency. And this is going to be computed assuming that, I wonder, oh, hold on. I think I can do something here. This will be fun. Assuming that, draw. This will be assuming that the row and column variables are independent. So for each entry in the table, we'll be able to compute the expected frequency, assuming that the rows and columns are independent. R is the number of rows in a contingency table, not including labels or row titles. And C represents the number of columns in the contingency table. So in our case, oh, okay, mouse. So in our case, oh, that's goofy. So in our case, R, the number of rows is 4, and C, the number of columns is 2. So I'm going to go back and take a look at the chat, see if there's any questions so far. No questions so far? I assume everybody is seeing and hearing everything okay. So let me know on the chat if that's not the case. Okay. So just like with all of our other hypothesis tests, we have a null and alternative hypothesis. The good news for this homework assignment is that this step is going to be easy. I think previously, sometimes it's greater than, sometimes it's less than. In this chapter, the null hypothesis is always going to be this sentence: the row and column variables are independent. The alternative is that the row and column variables are dependent. So that'll always be the same in chapter 11-2. Anytime we're doing a test for independence with a contingency table, this H naught will always be the null hypothesis. I mean, the row and column variables are independent. It will always be the null hypothesis. Row and column variables are dependent. Will always be the alternative hypothesis. Now, quick recap from chapter 4. Again, if we were having a final, I like to cover this section just because it forces us to review a lot of these things from long, long ago, like a month. So the probability of A and B, this is in your notes, a month ago, is the probability of A multiplied by the probability of B given A. Now that's in general, right? But specifically when, you know what I can do? Okay, but specifically when A and B are independent, you can safely say that the probability of A and B is the probability of A multiplied by the probability of B. So let's see, what in the world does this have to do with our example? Well, assuming that A and B are independent, that's the equation that we just saw. What are these 3 probabilities? So here's a quick review. Oh, you can already see the answer. Dang it. Okay, so assuming that A and B are independent, the probability of A and B equals probability of A times probability of B. What are these 3 probabilities? If A equals probability of surgery, and B equals the probability of success. I assume you can see the slideshow and you can see my face right now. Let me know if that's not true. Okay, so I wanted to give you a chance while I was erasing for you to think about these questions. So, for example, what is probability of A? So the probability of A is where A is surgery. So as a quick review from chapter 4, the probability of a surgery based on this table is going to be coming from that first row where you see a 54 and a 12. So the first question I would ask is, what's the total number and then the number of surgeries. That's our usual thing that we would have done back in chapter 4. And in this particular case, if you haven't guessed already, the total number of procedures is going to be the total of all 8 of these frequencies. So what is that? 54, 41, 70, 17. Okay, I guess I did the math previously. You can double check me on that. But if you add up all 8 of those numbers, I think you get 253. Total procedures were included in this research. And out of those, the number of surgeries was 54 plus 12. Some were a success, some were a failure, but in total, that's 66 surgeries. Okay? Similarly, P of B, also known as the probability of a success, similarly, it's going to be the total number of procedures, and then among those, how many were a success. So in this case, I'm ignoring what procedure was chosen. I just want to count how many people had successful results. So in this case, we had, again, 253 total procedures, but out of those, how many of those were a success? Do you see where that 182 comes from? The 182 is the sum of all 4 numbers in the first column. So these are all things that, so the procedures I'm going through here is more to review from chapter 4. If we were taking the final, these are the sort of things I would expect you to be able to do on the final. And in case you're just joining us, if you missed the announcement at the beginning, I did put an announcement on Canvas giving you the option of taking the final. If you choose, you just gotta send me an email and let me know that I should expect you, okay? If I don't hear from anybody, then I won't prepare a final. And last but not least, we have the probability of a successful surgery. That's the probability of A and B. So if A is a surgery and B is success, then P of A and B would be a successful surgery. Again, out of 253 procedures, how many of those were successful? And I think that's just going to be actually literally just 54. Now, when you look at these numbers, if A and B are independent, then that means, right? If A and B are independent, then that means that this number, P of A, multiplied by P of B, should be equal to that number, the probability of A and B. And that's coming from the formula that you see at the top. That's if they were perfectly independent. And so what I did is I took, as you can see on the slide, I took the 66 over 253 and multiplied that by the 182 over 253. And if you multiply those together, you get 0.188. Now compare that to 54 over 253, you get 0.213. Those are not the same number. So based on what we said in chapter 4, we would have said they are not independent. In other words, that they are dependent. But then again, the fact that they're close might, the fact that they're only slightly off could be due to sampling error. So as usual, we're asking whether the difference between the 0.213 and 0.188, is it a significant difference? So I'm trying to emphasize the language that we've been using in chapters 8 and 9 regarding hypothesis testing. So it is possible that the difference is due to sampling error, and so it is possible that the variables are still independent. All right, so for the next couple of slides, I want to actually I'll check on the chat after I say what I want to say, and then we'll come back to the slideshow. But I want to say that the next couple of slides, there's a bit of algebra involved, and in case I lose you, I have good news. At the very end, I'll show you a sequence of buttons you can push on your calculator, and it'll do everything I'm about to do for you. All right, so in case I lose you, don't worry. We have a backup plan. So let me take a peek at the chat. Okay, I don't see any new comments in the chat, so I'll assume everything is okay so far. Okay, and so coming back to here, okay, yeah, do this button again. All right. All right, so let's see here. So yeah, so again, as you can see, if the probability of A and B, if you take a look at this, the key, there's a lot of algebra going on right here, but the key, what I really want to draw your attention to, I'm trying to calculate the total number of successful surgeries. Like if this was perfectly independent, then I want to see what can I expect to be the total number of successful surgeries. So let's see here. My annotation isn't coming up. Oh, there it is. I can do this little thing right here. So this is really what I'm trying to get at, is this part right here. If you recall a few moments ago, I was making a distinction between the observed frequency and the expected frequency. So right here, we observed 54 successful surgeries. But if under the assumption that the treatment is independent of the results, or the results are independent of the treatment, maybe that's a better way of saying it, what would be the expected number of successful surgeries? And so we know that the actual number of successful surgeries was 54, but leaving that as a variable, it can be shown that the expected number of successful surgeries should have been 47.48, and which is kind of weird. Like you can't have like 47.5 successful surgeries. But for the purposes of our computation, we can look at this as the theoretical expected number of successful surgeries. And what we have to do is we have to repeat all these computations for all 8 of these entries. And we're going to compare what was observed to what was expected and see if it's a significant difference. Let's see here. Okay. Oh, I got to go back to here and do this. Okay. Let's erase that. All right. So assuming that A and B are independent, the expected value can be computed by taking the row total multiplied by the column total divided by the grand total. So you can see how, if I go back to the previous slide, basically the 66 was the row total. 54 plus 12 is 66. The 182 is the column total. 54 plus 41 plus 70 plus 17 is 182. And the 253 is the grand total. And that's where that expected number came from. And the test statistic is going to be computed via the chi-square distribution. So we worked a bit with chi-square before. The sigma means you're going to be adding up a bunch of stuff. And that 47.48, okay, well, actually, I got to show a couple steps. So those will be on the next slide. But assuming that the sample data is randomly selected, sample data represented from frequency counts in a two-way table, as in our example, and we have expected frequencies that are all at least 5. Those are the key requirements to do what we want to do. So I mentioned before that lowercase r is the number of rows, lowercase c is the number of columns. In our example, the number of rows is 4, so 4 minus 1 is 3. And in our example, the number of columns is 2, and 2 minus 1 is 1. 3 times 1 is 3, so there's going to be 3 degrees of freedom. And tests of independence will always be right-tailed. Oh, nice, I hear some music. Let me check to see if there's any questions on the chat. No new comments? Okay. And let's see here, we come back to here. Okay. So yeah, so as it is, this is presumably the data are randomly selected. The data, sample data is represented in a two-way column. That was the second condition. The third condition is the one you need to pay attention to. You might come across this in the homework tonight. For every cell in the contingency table, is the expected frequency at least 5? Now, at a glance, I look at all these frequencies, and one of them is smaller than 5, but that's okay because this is the observed frequency. I need to compute the expected frequency for all 5 of these and make sure that all the expected frequencies are greater than or equal to 5. So let me show you where these numbers come from. So take, for example, so how many surgeries were a failure? Failed surgeries. If you look at the table, we can see that there was 12 failed surgeries. And so O equals 12 in this case. The question I want to ask now is, assuming that the result of the surgery is independent of the procedure chosen, what should the number of expected frequencies have been? So ultimately I want to see how far off is what was observed from what was expected. And what we saw on the previous slide is that you could take the row total multiplied by the column total divided by the grand total. And in this case, do you see what numbers I'm about to drop here, here, and here? I'll give you a second to kind of think about that, to look at the table and see what numbers go where. I'll start with the bottom. That's usually the easiest one. What's the grand total? In this table, I've actually included the sum of the success column and the sum of the failure column. And if you take 182 plus 71, you get 253, as we've seen previously. The row total, that's the row total that includes the 12. So that the row total for surgeries was 66. And the column total for failed surgeries is 71. And if you take, oh, look at that, clear. And so, using your calculator, you can take 66 times 71 divided by 253. And it ends up being about 18.52. So although 12 failed surgeries was observed, if the procedure was independent of the results, you would have expected more like 18 or 19 failed surgeries. So what was observed was actually below what would have been expected, actually. And this whole procedure has been repeated for all 9 entries. And I'll go ahead and point out, remember how for non-weight bearing casts for 6 weeks, 3 of those procedures were resulted in a failure. If this was a completely independent, then we would have expected 20.49. And that 20.49 came from 71 times 73 divided by 253. So again, we mentioned before, I was a little worried because the third requirement in order to do a test for independence is that each of the expected frequencies needs to be at least 5. And as I look, that's bigger than 5, 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 that's bigger than 5. Everything's bigger than 5. So the third condition is met. The null hypothesis will always be row and column variables are independent. The alternative is that the row and column variables are dependent. Now, this step is actually pretty time consuming if you're doing it by hand. But what's happening here is I'm taking, for each of the 8 entries in the table, I'm comparing what was observed to what was expected. In the first case, we have 54 observed successful surgeries compared to the 47.48 expected successful surgeries. O minus E squared means you subtract those numbers and square the difference. The E means divide by the expected number, not the observed, but the expected, 47.48. And you do that each step along the way. For example, for weight-bearing casts, 41 observed successes compared to the 66 expected. If you square the difference and divide, you get 9.58. And the dot, 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 just, I just didn't take the time to do that literally for all of them. But if you did, the sum of all these expressions, remember sigma means sum, will add up to 58.39. So if you're gonna, there might be some exercises where they ask you to do that by hand. So that would be what? Open parenthesis, I would say, 54 minus what? 47.48? Divided by, yeah, 47.48. You get about 0.895. Okay, I guess if I round off to the nearest tenth, the 5 after the 9 says round the 89 up to 90. That's where that came from. You just got to do that 8 times and then add up the 8 numbers. You get 58.39. I'm going to take a peek at the chat. No new comments. For all I know, maybe everybody fell asleep. Anyway, but again, if you have any questions, feel free to type them in, or you can even just speak up, and that's fine too. Okay, so where were we? This one I'm looking at? No, this one? Yes. Okay, so yeah, so it's a bit of work. I've only really just given you a couple steps of it to come up with that number. But I see. Oh, there's an alert. It says there's a chat question. I'm awake. Okay, great. Thanks for the confirmation of awakeness.
Mm-hmm.
And yeah, LOL, not sleeping. Very nice. All right, it's okay. You won't hurt my feelings if you are sleeping. All right, so yeah, so this is the, so with the degrees of freedom is R minus 1, C minus 1, so 3 times 1 is 3. You can compute the p-value, and that's using the chi-square CDF. So that was 58.399. Remember that one? Distributions. We've used the chi-square CDF whenever you're calculating the p-value. We've done that before. So going down to there. The lower, okay, what is this? So the picture that I have in mind, let me go ahead and draw the picture. The picture now is not symmetric because it's a chi-square distribution. The picture is going to be going that. It's a right skew chi-square distribution. The distribution begins at 0. So very different from your usual normal distribution and your usual t distribution. But for these tests of independence, these tests for independence will always be right tail. So when chi-square is 0, that means it's perfectly independent. Like all the observed and expected frequencies were completely, everything that you expected is what happened. The further you are away from 0, the more evidence there is against the null hypothesis. If you're over here, that means that you're gonna reject the null hypothesis. In other words, you're gonna conclude that the variables are dependent. If the test statistic is over here, that would be insufficient evidence against the null hypothesis. You're gonna fail to reject the null hypothesis. So at this point, we have a test statistic of, let's see, where did it go? Our test statistic was 58.39. That's when we calculated this number right here. I like to abbreviate that with a TS, short for test statistic. Notice that this number came directly from the data, comparing observed to expected. And the p-value is the area of that tail. And so this also relates to the question that was asked earlier about the critical value. You might come across some homework questions where they ask for the critical value. Well, that's kind of like I said before, but it'll always be a right tail test. And it's just gonna be, you're gonna require that the area be 0.05, for example, and then figure out what value of chi-square would cut off that area. So again, there's always 2 ways of reaching the same conclusion, at least 2 ways. And with this picture in mind that I reach for my calculator, and I have as my lower bound, that is to say the lower bound of this shaded region is 58.39. That's where the shaded region begins. The upper bound is just, technically there is no upper bound. It's unbounded, it goes out forever. So just plug in something huge. That should be big enough. And then the degrees of freedom, that's when you got to remember this formula here. the number of rows minus 1, the number of columns minus 1. In our example, the degrees of freedom is 3. And that's our p-value. Make sure you read all the way across the screen. The most important detail is right over there. 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 8. So very small number. Very small number. And just like in chapter 8, just like in chapter 9, when the p-value is small, we reject the null hypothesis. Okay? In other words, there's insufficient evidence to say that these variables are independent of each other. It appears that the result of the surgery does depend on which procedure you choose. So yeah, so at the 5% level of significance, there is sufficient evidence to suggest that the success of the treatment depends on which treatment is chosen. So because this is clearly smaller than 0.05. And if you had a stress fracture and a foot bone, which treatment would you prefer? Well, since it depends, then that's an important decision to make. If it didn't depend on the procedure, then you can just pick something more or less at random, I suppose. Anyway, I can see now that there's a little alert that pops up if someone has a question. So if you have a question, just go ahead and type it in the chat, and I should see an alert. Anyway, I think we're just about through this, and so this is a picture that I've just drawn at the 5% level of significance, the critical value. Okay, so let's review critical value again. For a right cell test, the critical value. Let me erase this now. The critical value is going to tell you exactly how big chi-square needs to be in order for me to decide to reject the null hypothesis, in order for me to decide that these are dependent. And the way we do that is we require that the area is 0.05. And the critical value is the value of chi-square that would cut off that much area. And I think, let me go ahead and say this. I think I have, so since usually I would pull it up in the class, but I think I can pull it up now. Your green cardstock is what I'm referring to. Perhaps you have it handy, so you'll probably find it faster than I can. I'm just trying to remember where I saved it. Exams, labs, reference probably. There it is. So here's your cardstock, and then as you can see in our example, we have 3 degrees of freedom. And I want the area to the right to be 5%. And column headings are areas to the right. So therefore, I'm going to be interested in this column right here. And with 3 degrees of freedom, that's my critical value. In summary, when there are 3 degrees of freedom, that's how far from 0 chi-squared would have to be in order for me to conclude that I would reject the null hypothesis. If it was to the left of 7.815, I would fail to reject the null hypothesis. I'd say there's not enough evidence to decide that it depends, that these variables are dependent. And yeah, so you'll have a link on the homework to see the same table if you don't have the green cardstock handy. And there you can see the same number right there that we just computed with the table. Same sort of things I just wrote on the board as well. Reject independence, fail to reject independence. Okay. So here's the part you're going to like. Okay. This is, if you were taking a final, this is what I would recommend. If you're doing this in a pinch, is how to do this on your calculator. So I'm going to go ahead and demonstrate this right now. You can see the instructions. We're going to begin by going to, you're going to begin by pressing a button you're not used to pressing, at least in our class. It's a matrix button, edit 1A. So I'll go ahead and demonstrate that for you now. I'm going to go to, and please follow along if you have a calculator handy. So matrix, if your calculator is like mine, it's right over here on the left-hand side in blue, written above the x-1 button. Matrix, since it's blue, I'll begin by pressing second. Matrix. So there's names, math, and edit. I'm going to go over here. And okay, so you can see I already did a trial run already. And but for you, it's probably blank. So you're going to begin by typing in 4 and 2. And you're going to have all zeros right there. But what you're going to do now is you're going to transcribe each of these numbers into the matrix, just the way you see it. So 54 here, I'm going to put a 12 next to it. 12. Next one's going to be a 41 and a 51. 70 and 3. You'll be doing something similar in the homework. 17 and 5. And so matrix A, it consists of all 8 of those numbers. It's literally the contingency table. Okay. Any questions so far? So the next thing we're going to go stat, tests, chi-square test. So stat, we've been here many times before under tests, but the option I want you to choose isn't in here. You have to keep pressing down past 9 and you'll see that there's some more options. There it is. There's a lot of other ones. We're not doing the goodness of fit test, but letter C is the chi-square test. And as you can see, observed is A. You could have chosen a different letter other than A for your matrix. If you did, then make sure that you have the right thing there. And then the expected is going to be computed automatically in another matrix. I'm going to just let it be B, just something else. And a lot just happened at the push of a button. You remember the 58.39? Where did that go? Remember a few moments ago, we calculated where did that go? 58.39, that was our test statistic. So the calculator did that for me. Also, eventually, after we had the test statistic, we plugged that into the chi-square CDF and got this. Oh, it looks a little different. 12, 15. Okay, maybe a typo. All right. Well, anyway, as you can see, there's going to be the p-value was computed automatically, and so that's going to save you some time. But of course, as you've seen on the 3 exams, if you're taking the final, I like to see a little bit of evidence of understanding the procedures and also understanding like the numbers once you compute them. So, and I'll show you one final thing. It's not written on here, but if you go back to matrix again, second matrix, it automatically created a matrix B, also a 4x2 matrix. And if I go to edit and select matrix B, press enter, see that? I don't know if those numbers look familiar. Should though. Remember the work that was required? We never actually did all 8 of these, but we did at least 2 of these. That was the O minus E squared divided by E. And that 47.48 is what you see right here. So the calculator automatically took the row total, the column total, and divided by the grand total to get 18.52 and put it right there. The calculator automatically grabbed the row total here and the column total here, multiplied and divided by the grand total to get 66.18. That's what you see right there. So pretty convenient. At the end of the day, you can let the calculator do all the heavy lifting. So yeah, so in conclusion, we're always comparing the observed to what was expected. And if these are very far apart, it's going to push the test statistic further to the right. And if it's far enough to the right, we will reject independence and decide that that it does actually, we reject independence. We say that there's sufficient evidence to say that the results depend on the procedure. And that concludes that particular slideshow. So hopefully that's enough to kind of get you going. Taking a peek here, once again, at this. What am I looking for? I'm looking for this, I think. So as you get started on this, you can expect some questions that are related to what we just talked about. We won't necessarily have to do a surgery and whether it was a success or not. It could have to do with a polygraph test, which is a test that detects, the idea is it's supposed to be able to tell if you're lying or not. And then if I had some way of knowing whether they actually did lie or not, you can see that the polygraph test is not perfect. But is it good enough that your answer depends on whether you lied or not? Well, you can do a chi-square test to investigate that. Results of a civil servant exam are shown in the table to the right. Is there sufficient evidence to support the claim that the results of the test are discriminatory? White candidates, minority candidates, whether they passed or failed, does passing or failing depend on your race? You're going to make 1 or 2 decisions, either that they're independent or dependent, one or the other. Guilty plea, not guilty. Does your plea make a difference as to whether you're sent to prison or not? Is it dependent or independent? Soccer, if you kick left, center, right, and the goalkeeper jumps left, center, right, are these independent or are they dependent? So you can kind of see a theme there, right? Anyway, are there any other, I think I'll leave it at that for now. Keep checking the announcements. I haven't decided yet if I'm going to hold a session tomorrow. I think I'll probably at least do an office hour in case anybody has any questions, but we have no new material to cover. So I think, yeah, I'll just go ahead and make that official right now. I'll go ahead and do like some sort of an office hour session tomorrow. If anybody has any specific questions, then send me a message and we can set up another, I can either answer the question by email or we can set up a one-on-one sort of Zoom meeting just as well. So we can do that this afternoon, and at our usual class time, I'll set something up for tomorrow. But if there's no more questions, well, then I'll be concluding this meeting. Any more questions?